Let's remember some things from last time because we're going to use them more today. So first things first, here is a triangle with angles and sides labeled accordingly. The area formula we got yesterday, what does it say the area of this triangle is? I think there are 3 different right answers.
1/2 of z times y times the sine x.
That's if you use the area formula centered there. You could equally well center it anywhere else, right? It's a triangle. You could rotate it so a different angle was in the bottom left corner. So this should give you the same as 1/2, I don't know, zx sine y. In fact, just based on that fact, you'll be able to get the law of sines. And let's just recall what the law of sines says. So what does the law of sines say about this triangle?
Sine of x over x is equal to sine of y over y. And is equal to the sine of z over z.
Well, I've tried to be very clear which of those are the lowercase and which ones are the capitals. But I guess it's reasonably clear the things that you take sines of had better be angles. You probably shouldn't be taking the sine of a side of a triangle unless you have a good reason to. So one thing we did yesterday, the very last thing, is we said, well, that means that if you know like those two numbers and you know the area of the triangle, you should be able to conjure up what x is by using inverse sine. But as we saw, it turns out there are 2 different solutions. And what are those 2 different solutions? There is, if you use arc sine to get an angle in a triangle, we'll only report an acute possibility. So the acute possibility so, if you know what the sine of an angle should be, you should be able to get that angle by doing inverse sine to it. So there's like a whole sentence inside there. I didn't have a variable name in mind for what you know sine of A should be. If you know what sine of A should be, then A should be inverse sine of that. Except it might not be. There's a second option. It might also be pi minus the acute option, or 180 degrees minus the acute option if you're walking in degrees. And notice the big old if there. If that angle has the possibility of being obtuse, which sometimes it can't, then you don't have a second option. But if it can be obtuse, then there's a second option that sine doesn't see, inverse sine doesn't see. So here's the main takeaway, and we will hit that point several times today. When using arc sine or inverse sine, if you prefer, to find an angle in a triangle, so there are 2 things you need to worry. One is there an obtuse option? And second is, how do you find it? And how do you find it is the thing right there. So I think the best way to illustrate this is let's just do some examples. So kind of the point of the next couple of days, well, today, yesterday, and Monday, is if you know 3 facts about a triangle, you probably know the triangle. And we've already seen that once. If you know 2 angles and a side, you can find the missing angle, and then you can use law of sines to find the missing sides. Let's go the other way. So let's suppose instead that you know 2 sides of a triangle, and you know the an angle, but not the angle at which they meet. Let's try to solve this triangle problem. And the first thing to worry about is, can you use the law of sines to tell you things about this? And I think so, because the law of sines says if you know an angle and a side opposite, and then something else, you should be able to solve this stuff. Do you know a pair consisting of an angle and a side opposite? Yeah, so let's start with that. So you know for a fact that sine of 60 degrees divided by its opposite side length 10 is equal to, and now I'll look for a pair where I know one or the other. So between big A and little a, I don't know either of those, so law of sines won't be useful immediately. Between little c and 11, oh, I know one of those, is equal to the sine of little c divided by 11. Feel pretty okay? Nice. That looks like something you can solve for sine of c. There, right? Given that equation, what is sine of c equal to? And I'll be happy with exact answer simplified or not. I'll be reasonably happy with the decimal approximation. I'll want it anyway.
Equals about 0.9526.
Cool. So I hear sine of c is approximately, you said 0.926?
9526.
9526. People agree with that? All right. Let's also write down the exact value. So what did you plug into the calculator to get that?
11 sine 60.
Cool. 11 times sine of 60 degrees divided by 10. All right, you just need to cross multiply that 11 in the denominator. We do have, this is a super not deeply relevant point. Do we know what the sine of 60 degrees is? Is that on the unit circle? Yeah, so we could get an exact value that's more simple than this without a calculator. What is sine of 60?
Root of 3 over 2.
3 over 2. So I could have written that as 11 root 3 and then divide by 2, so divide by 20. Nice. All right, cool. So that means sine of c is equal to that number. So how do you get c itself?
Inverse sine.
Inverse sine of that number. So c is then equal to sine inverse, and since I want exactly equal to, I won't use the decimal approximation. 11 root 3 over 20. And now if we want a decimal approximation, we can get one. What is that about?
72.3
72.3
degrees.
degrees. Which degrees is the appropriate choice because we have some information in degrees. But if you have some angles in degrees, you probably don't want some of the angles to be in radians. That's just a recipe for confusion. All right, nice. That feels pretty good. So here's the thing to ask then. This angle C, we found it using inverse trigonometry. So since we used inverse sine to find it, we need to worry about whether or not the angle C might be obtuse. And here is another big takeaway from these notes that are kind of
hidden, so I'm going to circle it because it's important.
If you have an angle in a triangle that is opposite the largest side length, then it might be obtuse. And that makes sense, right? If you had, whenever you have an obtuse angle, the opposite side length will have to be the longest side. So let's just ask about this. The side length opposite C, is it possible that that side length might be the longest? So it's possible that the angle C might be obtuse. How do you find the obtuse choice?
180 minus 72.
180 minus that angle.
So there's a second option. Might A be obtuse? Yes. So let's write down both of those. So one of them is the angle we just found. And you know what? I'm going to jump down to the decimal approximation. I think things will be easier to follow. About 72.3 degrees, or about 180 degrees minus 72.3 degrees.
And you know what? I guess I just have to know what that is. (180 degrees) minus arc sine of 11 times square root of 3 divide by 20, all that inside of the arc sine, and Google will default to thinking that I want things to be in radians and I don't know how to tell it otherwise. So I'll convert to degrees. And then it just won't do it at all anyway. Alright, that agree with what other people got on their own quicker? 107.7? And I guess in that time I could have just done the subtraction by hand. So a thing to remember is this is an approximate value and not exact. And there's no hope of me getting exact values at this stage unless I fill in those preceding lines and use that. But let's look at what we have. We have now this triangle in two cases. Angle A is unknown. Side length big A is unknown. 10, 11. This angle is 60 degrees. That angle, I don't have space to write, is 72.3 degrees. The obtuse choice, I'll draw it like it's obtuse. Side length 11, side length 10. Angle of 107.7 degrees. Angle of 60 degrees. And then the same unknowns. A. In each of those individual cases, could we find the angle little a? Set that on. In each of those cases, we can find the angle little a. Because what do angles in a triangle have to add up to? 180 degrees. Yeah, so we can use that. So, angle little a plus 60 degrees plus this angle C that I'll just fill in the last step has to add up to 180 degrees. It looks like A is 120 minus C. Groovy. People feel pretty good about that? Nice. So, there's going to be plenty of calculator use opportunity today, so if you're like holding off on taking a calculator out of a backpack, you may as well do it now. So I'll go ahead and do that same calculator-based computation. I guess I've already got Wolfram Alpha up, may as well use it. 120 minus and I could be using exact values here, but I think I'm okay with rounding things off to the 10th. So, about 47.7 degrees. Does that agree? Have I done anything wrong yet? Okay. So, that angle A is about 47.7 degrees. I'm going to jump over to the other side of the paper. in the case that C was obtuse, we'll get a different value for A, I think. In fact, get that different value for A for me. What do you get? I hear a 12.3. Do I hear a second? Nice.
So in this case, the angle A is about 12.3 degrees.
Awesome. All right, so we have these two different triangles. They have
An acute and an obtuse option. The resulting thought angle A
is different depending on which one that was. We still need the side length big A. What's the strategy we should use to find big A? Gesundheit. Yeah, I know the things to use law of sines, right?
So the thing I would like to know is big A. I'll use the version of law of sines that has the sides on top. A divided by the sine of little a, and I know what little a is. It's this, is equal to,
Now I need to pick a pair consisting of a side and an angle opposite that I know. Which pair should I use? 10 and sine 60 seems to make sense. I could also use like 11 and the angle little c, right? Here's why I wouldn't want to. I only know the angle little c up to some rounding. So I shouldn't trust that as much as I trust Gesundheit, the 60-degree angle. So I'll use the one that I know with more precision.
gosh, and that's 10 over sine 60 degrees.
And there's going to be lots of decimal approximation anyway, because right now I only know this up to an approximation. Yeah. Oh, like if you started with the reciprocal instead? Oh, maybe people will walk. But we can go through that on the other side if you do set it up that way, what the extra bit of walk is. Because there's enough space for something to go wrong. And it's something that I saw go wrong on several people's exam, like messing with the fraction and just doing something fundamentally wrong in the fraction of doing a trigonometry. So we will do it the other way on this side. Let's finish this one out first. Could you solve that for capital A? Yeah, you just need to multiply the sign of the thing in the denominator needs to go on the other side.
So A is 10 sine of little a divided by sine of 60 degrees. And I know what A is approximately. It's 10 times the sine of 47.7 degrees divided by sine 60 degrees. And notice I'm doing something here. I'm giving the exact value right there, and then also the approximation next to it. So if I go and resolve this problem and find out that I'm not within the margin of error that I need, then what would I do? I'd go back and record the initial angle A to more precision. I then have the exact value, C to more precision. I have the exact value for A, so I can now find an approximation for it with more precision, which I can plug in here. But in the meantime, I think I've stalled long enough.
In the acute option, what is A, give or take? I guess I can compute it too, but.
Oh, 8.54.
I hear an 8.54. Nice. Have we now found all of the facts out about this triangle? Wait, what do we not know yet?
Sorry. No,
Yeah.
I thought you meant the other.
Oh yeah, we still need to do the other case. Yeah, so really, there are two triangles described by the starting information. We've totally described one of them. There's one more fact we need about the other side. And let's do the other side, and just for the sake of demoing what happens if you make a not incorrect choice, but a strategically more difficult choice, let's see what happens if I use the other version of law of sines. I'd see sine of little a over big A is equal to the sine of 60 degrees divided by 10. There's another statement of the law of sines. In fact, that's the one on the board. And I want to solve that for big A. What would you need to do that?
cross multiply.
Yeah, cross multiply. Right, the big A is in a denominator. I need it to not be in a denominator. So let's cross multiply to get it out.
So if you cross multiply, you'll get 10 goes to the other side to be 10 multiplied by sine of A. Big A goes to the other side, becomes big A sine of 60 degrees.
And now what do you need to do if you want to get big A on its own? Divide by the thing next to it. So, doing that,
10, that's a multiply sign, not a subtract sign. 10 sine of A divided by sine 60 degrees is equal to the side length big A.
Oh, cool. Does that look like the same as the exact value we got on the other side? Yeah, and that's like kind of handy. That just means I need to sub out the value for the angle little a. And what do you think? Did that make sense algebraically? Yeah. And you have these extra steps, so it's harder, but it's not long. Cool.
Let's get that decimal approximation. So that's about 10 times sine of, I have a different value for A, 12.3 degrees, divided by sine of 60 degrees. And I'm sure you all have that computation at this point, but let's do it. Pull that up, put it to the side where it's not covering up the thing I need to see. 10 multiplied by sine of 12.3 degrees divided by sine of 60 degrees. That agree with people's calculator results? Nice. So the side length A is about 2.46, I guess that rounds up.
And let's just check one last thing. Are there any units that I should be worried about in the problem? Do the side lengths have any units on them, or are they just abstract numbers? Just numbers? Okay, cool. So no units. That process feel pretty okay? Nice. So, what do I want to do with a chunk of the rest of today?
So here's one case based on this fact.
If the angle opposite the unknown angle might be the longest side, then that angle might be obtuse. Law of sines won't tell you if it's obtuse or not, because sine doesn't know the difference between acute angles and obtuse angles. Cosine does. We'll find that that's useful on Monday. So let's focus on that on the next problem too. So the next problem will look very similar, but something fundamentally different will happen.
All right.
So, similar looking problem. Let's see what headway we can make. And you know what, maybe I'll see how people feel about walking independently
Or with each other. I would like you, if you could, you know what, to get so far as like there.
And especially on that yes/no question, discuss with those around you once you get to it. stuck and want me to like give some guidance. Okay, cool. Yeah, so let's, I think a picture will help. So I'm going to draw a picture of a very obtuse angle. So obtuse just means bigger than 90 degrees. So here's a very obtuse angle. In looking at this triangle, which side is the longest side? So here's another way of saying this back. If the triangle has an obtuse side, an obtuse angle, then the longest side has to be opposite. So that means if you have an angle that you're worried about whether or not it might be obtuse, look at the side opposite. If it can't be the longest side, then that angle cannot be obtuse. Is that clear my way of saying it? Yeah. Okay, cool. Yeah, so take a look at the triangle in question. The unknown angle you're thinking about. Is it possible that the side opposite might be the longest side? And if the answer is yes, then the angle might be obtuse. If the answer is no, the angle cannot be obtuse.
So if the angle can't be obtuse, do you still have to compute the obtuse option?
No. Very simple. And maybe saying that aloud is also like a mild spoiler about the nature of this particular exercise. But hopefully most people are roughly at that point anyway. Cool. All right. So let's see what progress we've made. So you took a look at this triangle. Step one was not to determine what C is, but just to tell me what the sine of C is. And let's see, either decimal approximation or exact value will make me happy because I think I'm going to be approximate by the bottom of the page anyway. What is the sine of C according to this triangle?
Squared root of
3 square root 3 over. Do I hear a second? I guess that's the exact value. And maybe just to confirm, what decimal approximation did you get?
4 times 5. Or that is mine. That's for the
Ah,
0.65.
Cool. People feel pretty good right now? Anyone wind up with a different looking exact value but the same decimal approximation?
I need a different decimal approximation.
Ooh, different decimal approximation.
I'm probably wrong, but I got 0.0788.
Let's
Yes.
talk through it.
So, in order to find this, what equation did you write down?
I wrote 3 sine of 60 over 4.
Well, that might be what you wound up with, but you started with something like this probably. And then you multiplied the 3 over? Cool, I think I agree with that.
And then you used a calculator? Your radian mode? You're in degree mode, interesting.
I don't know if I punched it in wrong or something.
I'm thinking so. Because, right, what is sine of 60? It's root 3 over 2.
I forget to add a 0 in my calculator.
There we go.
Sine, 3 sine of 6.
Yep, there you go. All right, so, nice, we know what the sine of C is. And so we know what the acute option should be. It's the inverse sine of that.
Which is whatever decimal approximation you got.
So let's ask that yes/no question at the top of the page. Is it possible that this angle C might be obtuse? Folks who want to say yes? Folks who want to say no? Cool. Yeah, it's not.
And here's maybe the big takeaway here. If a side is not the longest in a triangle, then the angle opposite cannot be obtuse.
All right, so do I even need to fill in the rightmost column in this computation? Nope. Does not exist. And in fact, if you did fill it out, you would wind up with the angle little a being required to be negative, which at that point you would automatically know something's wrong. All right, cool. So, at this point we have the angle little c. In fact, what was the decimal approximation you got for angle little c? 40.5 degrees. Is that enough information that you can solve for A? Let's solve for A.
So I guess A had better be, I'll jump right to the approximation, 180 degrees minus 60 degrees minus 40.5 degrees. Is that 79.5? I want that to be 79.5. Awesome. Cool. So we know what the angle little a is. There's no second choice for little a because there's no second triangle. Could we find big A now? Yeah, like some law of sine stuff again. A divided by sine of little a will be the same as 4 over sine 60 degrees. And you know an exact value for sine of 60 degrees, but that angle little a, I don't think you can get an exact value for in any reasonable way. And you go and plug that value in for a, what do you get? Yes, I can do too. I hear about 4.5. I hear a second. Call for me to do the computation myself. Cool. All right. So, in this case, there is only one possible solution. The angle C had to be acute. That resulted in a choice for A that happened to also be acute, but there was no promise that A would be acute when we started. It might have turned out to be obtuse, and we wouldn't know till we got there. One last one, because something else funky can happen.
Let's try to solve this next triangle problem. So let's suppose you have a triangle, 60-degree angle here. Side of length 4, side of length 3. Let's see what we can do. So, same process, right? Sine of little c divided by 4 will have to be equal to sine of 60 degrees over 3. So sine of little c is 4 sine 60 degrees over 3. And right, we could replace that 60 degrees with root 3 over 2 and simplify, but I think I'm going to do something else instead. I'm going to just get a decimal approximation.
Says it's 60. Like, not the decimal, but the angle would be 60.
The angle C would be 60?
Yeah.
Ooh, I think something bad should happen first. So I'm going to carry on here and get this decimal approximation first. So it's 4 times sine of 60 degrees divided by 3.
I divided by 4.
Ah, that would do it. Yeah, because then you just have the inverse sine of the sine of 60. So it's about 1.15. And I know that this is a leading question because I only ask this question when the answer is yes. Did something bad happen here? Is there something bad about this? What's bad about this? Yeah.
They can be also.
Ooh, there's something even worse.
Oh.
It can't be obtuse because it just can't be.
It's bigger than.
Sine can't be bigger than 1. This triangle requires you to have an angle whose sine is bigger than 1. Sine of C cannot exceed 1. So this triangle cannot exist. And in fact, like take that 1.15-ish. If you take inverse sine of that, your calculator will throw out out of domain error. And so your calculator knows that this triangle doesn't have any solutions either. Unless your calculator is too clever for its own good and allows for complex angles, then it will give you like a complex number of the angle. Neato. Alrighty. People feeling pretty okay right now? So the thing I want to do to wrap up is I want to describe this with not quite a flowchart, but let's call it a guide. So I'm going to ask you on the web walk, and I don't know how many people have already looked at the web walk posted for this section. So you've already seen that there are some like solve these triangle problems questions. Okay. Hopefully this talk through this page right here will help with them. And you know, like, put off those questions for like 6 minutes.
Okay.
And then like go ahead and ask them while people are probably not, if you have time. If you have a triangle that you want to solve, and you are given two sides and then an angle not between them, thus the side-side angle, start by locating the known side length and angle opposite. In that case, that's those two. Next, locate the angle opposite a known side. Gesundheit. Well, those ones are dead. Put them in a place where I won't put them back in my bag. All right, and from there, do exactly what we did before. Write down the equation sine of b over b equals sine of a over a, solve for b, so sine of b is whatever it is you get. I'll write down what you get, but the main thing to know is that you just need to solve.
And this line will now be called star.
Does that line star say that sine of b is bigger than 1? If so, then you should just stop. There are no solutions. Sine cannot be bigger than 1.
Else, if b is not the longest side, then the angle b must be an acute angle. So b is equal to the inverse sine of whatever it is you got from step star.
That feel good?
If side length b is bigger than side length a, then angle b might be obtuse. So there are two possibilities, either the acute option or the obtuse option. Which is the same as the acute option, but 180 degrees minus.
Feel good right now?
And notice this is exactly what we did. I just want to write down the logs. And from there, you know what you need to do. Find the remaining missing angle. A plus B plus C will be pi radians, or 180 degrees. All of the examples today were in degrees, I think. But could we have done all of these examples in radians instead? Yeah, so just be aware. Then find the side length C using the law of sines. And the last thing I want to do in this particular pack of notes, and then we'll decide what we want to do with the remaining time. So for each of these problems, I don't want to find the solutions to these triangle problems. I haven't provided this space. I just want to know how many solutions I expect. And apparently, the options are no solutions. In the case that B must be acute, there's only one solution. If B might be obtuse, there will be two possible solutions. So for each of these questions, the answer is 0, 1, or 2. If I've designed the problems well, I better use each one of them. But let's go through and check each, and you know what? Let's see, do people feel like they would be comfortable with me just cutting them loose on one of those right now? Would people want me to talk through one before I make you do one? Cool. Then, here's what I'll do. I'll start talking on this option. We'll see what we get. Those of you who want to walk independently, well, no, just start on the same one, and then you'll just go faster. So, let's try to follow the same flowchart for this triangle. So step 1, locate a known angle and a known side opposite. Those are the ones that I know. Locate a known side with an unknown angle opposite. I'll use those to set up a law of sines question. So it looks like sine of little b over 10 is equal to sine of 10 degrees over 1.
Feel okay? That look like something you could solve for sine of little b?
Yeah, just multiply the 10 to the other side, and then you got to bust out a calculator. So sine of little b is equal to 10 times sine of 10 degrees. I don't need to worry about division by 1. That doesn't do anything. So I'll just forget the division by 1. And next, 10 degrees isn't on the unit circle. So I have this Gesundheit walking out to be about 1.7. All right, so that completes this step. Now I'll ask this question. Does that result say sine of b is bigger than 1? Can sine of b ever be bigger than 1? So how many solutions does that triangle problem have? Cool. All right. Do you think you can make some progress from there on your own? Yeah.
the one next one together, and then the remaining one, I guess you'll know what the answer should be because it'll be the option I don't use yet.
I don't know. Let's talk through this one. So, if the setup is the same, you need sine of b over 1 is equal to sine of 10 degrees over 3. Oh gosh, that's already solved.
Division by 1 doesn't do anything.
So I'm interested in the sine of 10 degrees over 3. Whatever sine is, it's less than 1, and 10 degrees is really small. So sine of 10 degrees will be small. I divide it by 3, it gets smaller. Is there any danger of this being bigger than 1? Nope. So I make it past this check. There are solutions, either 1 or 2. Might this side be the longest side? Nope, because there's a side of length 3. This triangle is not drawn to scale.
Alright. And how many people already walked out the middle problem as well? Did you get 2? Alright, good. That means I designed the problem correctly. At least for a problem in the notes. Like a homework problem, I can do whatever. Notes problem is better demonstrate each possibility. Yeah, there's whatever problem you want to do.
Yeah, oh, and that, and also, when's a good time, I think I'll see, I can't today, because, like, what's a good time to see about my test?
Yeah. Let's